sent a notification.
Oh, he's here, I think.
Yeah, he sent a new Zoom link.
It's the same Zoom.
Oh,
You hear me?
okay.
Are you
Hello?
hearing
Yep.
me, guys?
Yeah, I'm here now.
Yes.
Corey,
Make
you're
you-
actually here on time.
No, I'm not.
Okay, how many of you do I have in here? I'm sorry, my computer crashed on me. Do I have 18 people in here? We good? Guys, can you hear me?
Yes,
Yes.
sir.
Yes, sir.
All right, good enough. Thank you very much. And thank you for sticking around. I've just got to load this thing up again. I have no idea what was happening. And it's going to take a few minutes. I got myself another cup of coffee, though.
Me too.
Good for you. I'm glad you used your time wisely. And it's taken, every time my computer crashes, it takes forever to start loading up programs. Come on. Sorry, it's just taking a while to load up this PowerPoint. Thank you. Ah. Thank you. Technology, you gotta love it. Except I don't see the PowerPoint.
Yeah, I like it. All technology that isn't made by Microsoft.
You touched on Windows 11 yet?
No, actually, I don't have TPM 2.0.
My computer is constantly crashing.
Okay, you seeing the screen, guys?
Yes.
All right, you're seeing the PowerPoint? You're seeing the PowerPoint, right?
Yes.
All right, let's cut with the crap slides. Okay. Boiling point. Has anybody ever actually watched water boil? You're
Nope,
sitting
never.
there waiting for the pot.
Oh, yeah.
Yeah, you're sitting there. You see those little fake bubbles come up at first? Actually, what those little bubbles are the gases within the liquid bubbling away. But what you really want is you want the point where the water has gotten enough pressure that it is now at the same pressure as atmospheric. That is when you have the boiling point. It's the temperature at which the vapor pressure of your liquid equals the external pressure. So you got to increase the temperature up high enough so that you get this vapor pressure equal to the barometric pressure. So you're going to get into this hopefully in Chem 2. There are some things called intermolecular forces. And what the intermolecular forces are the attractions of one molecule to another one. Basically, all this semester and through intro, we've been talking mainly about intramolecular forces. Those are the forces within the molecule. These, when we're talking about intermolecular forces, this is the force between one molecule and its neighbor. And what intermolecular forces are responsible for are physical properties, such as boiling point, freezing point, and solubility. Now, what you have to realize, when you are at the boiling point, all the energy that you're putting in to the particular situation is going to make that substance a vapor. So because all the energy is going to change the substance from a liquid to a gas, all the energy is going there, the temperature doesn't rise at that point. So at the boiling point, you have a steady temperature. Now, if you're carefully watching this, what will happen is you put a thermometer into your situation. Now, the liquid will rise up. It's got a fairly hot temperature. The thermometer is relatively cool. So what the liquid does is it condenses on the thermometer. And eventually the drops get big enough that they start dripping off the end. So you've got an equilibrium eventually happening where you get the gas evaporating up, condensing as a liquid, then dripping back down. The temperature is not going to go up until all the liquid is in the air. And then you get a super hot liquid. Like, have you ever heard that you can get burned by steam a lot worse than you can by boiling water? Have you ever heard that?
I have scars to prove it.
Basically, what happens is steam can be heated higher than 100 degrees Celsius. So because of that, it burns you a lot worse. So the job we're doing in this laboratory is getting a liquid to get to the point where it is boiling. And we're going to notice that by a couple things. The first thing we're going to notice when we're looking at this is we're going to watch, as we're boiling this water off, we're going to watch the water condensing off the very end of the thermometer. And the other thing we're going to notice is that the temperature doesn't go up. When we are at that point, that means we are at the boiling point. Now, we can relate that vapor pressure with the temperature through something called the Clausius-Clapion equation. And that is the ln of the vapor pressure is equal to negative the heat of vaporization divided by R times 1 over the temperature plus the ln of B. Okay, B is a constant that's related to the gas. The delta H is the vapor pressure. I'm sorry, excuse me. The delta H is the heat of vaporization, which also is a constant. What you need to note down here, though, R is not 0.08206 because we've changed the label. It's not liter atmospheres per degree Kelvin mole. It's joules per mole degree Kelvin. If you take pressure times volume, you do work. When you do work, that means you are involving energy. So pressure times volume equals energy. We are able to convert that, those atmosphere liters, into something called joules. When we do that, we change the number of R to 8.314. All right, you got to note something though. This is important. Delta H is in kilojoules per mole. That's how it's reported out. R is in joules per mole. So you got to change one or the other. The easiest thing is to divide the R by 1,000. So you get 0.008314 kilojoules per mole Kelvin. Now, if we look at this, if we look at this equation, ln of P minus delta H over R times 1 over T plus ln of B. If we kind of look at it and decipher it, we can see the equation of a line. If my ln of P is my Y and my 1 over T is my X, then the slope of my line is negative delta H over R, and the y-intercept is the ln of B. Are you with me so far, guys? How many of you are going on to Chem 2? Get used to this. Get used to this, because you are going to constantly take things that you can't relate directly, and you are going to manipulate them such that you get an equation that is the equation of a line. The reason we are doing this, we can measure the pressure, right, guys? Can we measure the pressure? Shake your heads. Can we measure the temperature? So these are two things we can measure. If we measure them and make a graph, we can get the slope and we can determine something we can't measure, the heat of vaporization. Does that make sense, guys? You are going, this is part of what Chem 2 is. Chem 2, you will be manipulating equations rather than plugging numbers into an equation. That's why I like to use the analogy that Chem 1 is like jumping off the roof of your house. Chem 2 is like jumping off a 5-story building. You're going to have to learn how to manipulate equations. So we've just manipulated one. We have the ln of P. We plot the ln of P versus 1 over T. We're going to get a straight line. The straight line is going to have a slope, and that slope is going to be equal to negative delta H over R. Anybody have an idea? Is the line going to be this way, or is it going to be this way? This way, first way, or this way? When you plot ln P versus 1 over T, is the graph going to be this way, or is it going to be this way?
I'm going to say
It's
this
going to
one.
have a negative slope.
You're going to have a negative slope because your R cannot be a negative number, and your heat of vaporization, it takes energy to make something a gas. So that's going to be endothermic. So heat of vaporization is also a positive number. So you will have a negative slope with this. Okay, are we good with this? So this is going to be the graph portion of this experiment. All you're going to need to do is make a graph. You will get a slope of that graph, and you will take that slope, multiply it by negative R. That will be your heat of vaporization. Simple enough, guys? Okay, if we measure 2 points, if we take the 2 pressures or 2 temperatures, well, even if we do take 2 pressures or 2 temperatures, we still have 2 variables, right? Another example of how we're going to manipulate equations. If I have 2 variables, I got to get rid of one of them so I can solve for the other, right? Simple algebra, right, guys? So what I'm going to do is I'm going to measure 2 pressures and 2 temperatures, and I am going to subtract the two equations from one another. When I subtract the two equations from one another, the ln of B goes away. And I have ln of P2 minus ln of P1 equals negative delta HR times 1 over T2 minus 1 over T1. ln of P2 minus the ln of P1 is just simply ln P2 divided by P1. Anybody confused about the math? So basically, and I had to move you because I got to figure out what I'm saying down here. Oh yeah, I know what I did. This, don't worry about it. Don't worry about these last two lines. I can actually take them away. I was trying to illustrate something and I already done it. Ugh. That looks better. Okay. So what you're actually doing in this experiment, you're going to shove some liquid in a test tube. You're going to fit a test tube into a rubber cork and you're going to put it in the water bath and heat it slowly. The reason you're heating it slowly, you don't want to create any cannons. If you heat it real rapidly, pressure is going to rapidly build up and that cork and the thermometer are going to get impaled into the ceiling. So you're going to heat up this thermometer really, really slowly. And you're going to watch the thermometer for a steady temperature and you're going to watch for the water to begin boiling. You're going to watch for the condensation. Boiling points are hard to see. They're hard to detect. Normally, what happens is you record them as a range. You can see where it kind of starts to boil and you can see where the temperature starts to rise and go up beyond that. So that for a long time, the temperature is going to be fairly steady at a certain temperature range. Then once it gets beyond that, it's going to shoot up like crazy. So you've got a boiling range. So there are relationships between boiling points and heats of vaporization. You have a table on page 117 of your manual. What you're going to do is you're going to have your boiling point. You're going to go to the table and you are going to average your boiling point and figure out what your sample is and what your delta H is. All right, so we have a boiling point. Do we know what the pressure is at that boiling temperature? I mentioned it earlier, guys. What's the pressure when something is boiling?
The vapor pressure of water or of it.
Nope. No, it's not. It is, but there's a specific point that it equates with.
Atmospheric pressure.
Atmospheric pressure. Keep that in mind. This is going to be very important to solve these problems when you eventually get them in lecture. Because all they're going to do is they're going to give you the boiling point. They will not tell you what the pressure is. And basically, you're going to have to assume that the pressure is 760, which is normal atmospheric vapor pressure. So we know one temperature and one pressure. What the question is going to be asked is, what is the vapor pressure at another temperature? So we're asked at this point, what is the vapor pressure at 295 Kelvin? We already know our average boiling point is 65. So we add that to 273 and we get 338. So we looked in our table and found out what the heat of vaporization is. And that turned out to be 35.3 kilojoules per mole. So I simply have to plug in the values into my equation. P2 is what I'm searching for. P2 is going to be the vapor pressure at 295. It's extremely important to keep your parameters together. P2 needs to be associated with T2. The other one is 760 and 133. Solve this. You get the ln of P2 divided by 760 is equal to, that number is 4250. That turns out to be what these two numbers are. I multiply these together, I get negative 1.83. Now, after I get negative 1.83, to get rid of logs, what you have to do is you have to raise the base to that power. In other words, to get rid of the ln of P2 over 760, I have to raise E to the ln P2 over 760. E raised to the log equals, E raised to the ln equals 1. If I do that to the left side, I have to do it to the right. So I then convert line 4 into P2 over 760 is equal to E raised to the negative 1.83. E to the negative 1.83 is 0.162. I multiply 760 by that. My second pressure is 123. Couple of things you need to be worried about with the Clausius Clapion. Typical student errors. One, you don't realize that delta H is in kilojoules and R is in joules. One of them has to be converted to the other. Second thing, you don't relate the right pressure and the right temperature. Third thing, you get down to line 4 and you look at this and say, oh, this is the ln of P2 divided by 760. So you multiply it at this point by 760. That is not what the equation is saying. It is the log, parentheses, P2 divided by 760. As another sidelight, guys, if you are going on to Chem 2, please do your chemistry professor a favor. Review logs, because you guys notoriously do not know how to manipulate logs. I'm having that problem right now. This is just a slide to explain what I just said. Okay, so guys, what you're going to be doing is the student data will give you a boiling point. You're going to take that boiling point and look at the chart. You're going to determine what compound it is and what the heat of vaporization is. It's asking you to determine the vapor pressure at 295. Plug all the numbers into this equation and come up with a new vapor pressure. Any questions about the first half of this?
So is that number 123 the pressure in, yes, but is it in atmospheres or is it in?
No, Garrus, this number right here, that's torr. Okay? I could have put 1 atmosphere there. If I would have put 1 atmosphere there, then the number would have been in atmospheres. Whatever you plug in as the label of the pressure, that will be the label of the other pressure.
Okay. So we don't have to convert it to atmospheres?
No.
Okay.
No, you don't. Unless, Garrus, the problem specifically asks for atmospheres. You can solve it, save yourself a division, and just say, okay, this is over 1 atmosphere. Because if the problem doesn't state what label, you can certainly use 1 atmosphere. Your number is going to be very, very small, though. Just realize that. Any other questions about the first half of this? Okay. Second half is going to be a little more involved. It's going to be a little more monotonous, and it's going to be a little more tedious for you. On page 120 of your manual, you're going to find data of vapor pressure versus temperature. You need to convert all the vapor pressures to ln of P, and you need to convert all the temperatures to 1/T. Then you're going to make a graph of ln P versus 1/T. Use Excel. Now you get the graph. In this case, my slope is 4636.7. Once I get the slope, everything is a piece of cake because I know the slope is equal to minus delta H divided by R. I'm going to take my slope, multiply it by my negative R. That ends up being, it's a huge amount of joules. My huge amount of joules, I'm going to turn into kilojoules. This one, you do need to convert to kilojoules per mole because that's how delta H's are reported. Any questions, ladies and gentlemen? I am, because of the nature of this. If I don't see the points, on the graph, I will take off. Because as you can see, these are not exact. You have to estimate your best line as best you can. That means the more points you have, the more accurate your graph is going to be. I need to have all the LNs and all the 1/Ts. Questions about this? And I gotta move this. Okay, I gotta go back to. Oh, that's me. Why is this doing that? Oh, there we go. Yes, I can be trained. Okay. Getting into the actual guts of this. Student data. And we're going to go all the way down because this is the last one. At least I think it's the last one. There we go. That's all you need. You need to know the atmospheric pressure and the boiling point range of your liquid. We good with that? That's all the data you need from this. Okay. Getting back to table of contents. I gotta go through the lab man. Gotta go through the lab manual with you. Okay, not graphing. Okay, pre-lab, post. Okay, sorry. And you are going to be slow, aren't you? Hmm. Okay, boiling point. That is the table. That's the table you're going to look at to try and figure out what your heat of vaporization is. Record the data. That is, you've got 1, 2, 3, 4, 5, 6, 9 data points. I need to see them all in the graph.
I have a question.
I'm here, Garris.
Okay, I just want to make sure. So to fill in the table, for example, LNP, we would just put LN 9.2 in our calculator, right?
That's all you got to do. Put LN, hit 9.2, enter.
Okay.
Record that number. To do
And
the 1 over
temperature.
T, just put 1 divided by the temperature.
Okay. Okay, just making sure. Thank you.
No problem. Okay. Anybody have any questions about the data tables or what you're being asked to do? All right. I don't need that. I need this. Okay. Where are we at? Results. Start quiz. Okay. Simple questions. Always he asks simple questions that basically you can answer real quick and get points. So right away, you get 20 points right off the bat. Use the Clausius Clapion to determine what the vapor pressure is. Any questions about that one? Draw an Excel graph, upload it in here. Then figure out, if you're using Excel, and you are going to be using Excel, just put the slope in there and calculate the heat of vaporization. That's all to this lab, guys. Any questions about the results? Okay. I need to get into course content. Post-lab questions. Preview. Start quiz. I have to tell these things to myself so I remember them. Okay. Just give me you're given the known value is 44.1. Your experimental value is 48.07. Give me a percent error. Okay, I'm sorry. No, okay. You know, the boiling point is 84. You know, at 84, the vapor pressure is 760 torr. Figure out what the vapor pressure is at 25 degrees Celsius. This problem is the same one you're solving to do the first problem in our experiment. Third question, you have the heat of vaporization. Now you have the vapor pressure and the temperature of that vapor pressure. You're being asked the normal boiling point. You know at boiling point that pressure is going to be 760. Solve for C in that instance. Question 2, you're solving for pressure. 3, you're solving for temperature. While I've got you here, I want to talk about Tuesday's lecture. Tuesday's lecture is it's called Vesper, but in order to do Vesper, I need to teach you how to do Lewis dot structures. The lecture is going to be long. Normally speaking, it lasts an hour and a half to 2 hours, depending upon the class's understanding. All right, that's the first thing you need to understand. It is vital because I'm not sure you're going to get this in this much detail in your lecture. The other major thing about it, do you all remember the intro nomenclature lab? Do you remember that? Come on,
Yes.
shake your heads. Do you remember how long it was? Do you remember how long that lab was to do? Unfortunately, this one is almost as long. You're going to have 91 questions. Each question, they're going to be the same. They're going to ask you, how many lone pairs are there? Second question, I'll go through and identify how to do this. You're going to have 4 questions to answer for question 2. I will go through this next week. You're going to have what the electron geometry is, what the shape is, and is it polar? So you're going to have 5 questions. Question 2 has 4 parts to it. You're going to need to do this for divide 90 by 5, 18. 18 different compounds. You're going to be tempted. You're going to be tempted if you've done well in all the labs. If you have like a 90% average, or you're satisfied with your grade so far in all your reports, you are going to be tempted to avoid this because it is so long. I would suggest not doing that because it is good practice. You are not going to get this kind of practice in your lecture. So if you're going to drop one, drop the heat of vaporization lab. That one you probably, most probably, will not get tested on in your lecture. This one you will. And that's basically all I had to say. I wanted to give you fair warning about that and put in my pitch for you to do it. Plus, you know, it has the added advantage. This one is all multiple choice, so I don't have to grade it. Let's look out for Mr. Popovich here, right? Seriously, if you can, please do this laboratory. Now, I have an open period. Next Thursday, there's nothing planned. I will be here at a Zoom meeting. I will be here to discuss the final. Now, you have to prepare for that because my only advice for doing the final is to redo each individual lab. Take the raw data that's there and resolve all of the problems. That is the best way I can advise you to study for the final. Therefore, I'm not going to have anything prepared. It's going to be more or less a workshop next Thursday. Attendance is not mandatory. You can blow it off if you want. And literally speaking, that is all I'm going to do is I'm going to be there to help you work through the problems you're not understanding. I would go back, look at your former reports, see what you did well on, what you didn't do well on, and concentrate on what you didn't do well on. The final itself is fairly evenly distributed. Any other questions, guys?
I just want to clarify, when you say next Thursday, do you mean like next Wednesday during our normal
Yeah.
class time?
Sorry. Yes, sorry. My bad. Next Wednesday. That's all I got for you now, guys. Any other questions? People that are in my lecture, you realize that we are Zoom meeting tonight.
Yes.
Okay. So at least I'll have two people there, right, Kyle and Corey?
I'm going to show up to campus anyway.
Okay, that's all I have, guys.
All right.
Take care.
I'll see you.
All right, Professor. Thank you.
Take care, Jeremiah. I guess there's 3 people going to be here.
So when we're putting in the results and we need to use the Clapion equation,
Yep.
do we need to like write out the equation like ln p2 over p1?
Yep. You got to
Okay.
show your work, Eris.
And then for the table on the X and Y axis, are there any like units of measurement we need to put in?
For the ln of k, no. For 1 over T, it's going to be Kelvin to the -1.
Okay. All right. Thank you.
Good enough?
Professor, you took roles for me today, right?
Huh?
You
Yeah,
kinda-
exactly. You weren't there when I called your name, so I marked you absent.
oh Lord, I was probably making coffee.
Gates, if I take him roll this entire semester, I did at the beginning.
You
fine.
have, I think.
You're fine, Gates.
All right, thank you, Professor.
Ravina, do you have anything? Ravina, are you there?
No, I'm good. Thank you. I was just listening.
Okay, no problem.
Thank you. Bye.
Bye.